All right. So I apologize for having 2 lectures online in a row. A little bit out of my control. So also, I just realized yesterday that as an assignment for the first homework happened to be right on the deadline, happened to be right on the Valentine's Day. It was a little bit awkward. Hope we didn't spoil the celebration for you all. All right. So today we are going to study probably, how should I put it? Probably the most direct concept related to control. Like I call the lecture stabilizing control, but it is, just by the name you can kind of see it is as close to the core of the subject as it can get. And we are going to use the concepts that we developed so far to finally understand kind of the core idea of the course. Like we understood how you describe the systems, we understood the stability property of the systems, even how the system reacts to the input signal with body diagrams. Now we want to finally understand how we can control the system, so how to change its reactions. So that's what the lecture is going to be about. Now, let me, right from the start, just try to show an example and see if we are on the same page with what I'm talking about. All right, so consider this system. This is an autonomous LTI. Please remember the terminology, right? Why do I say it is LTI, linear time invariant? Well, because this coefficient does not depend on time. That's what it means to be an LTI. Why do I say autonomous? Well, because x dot equals to fx. This describes the system. Like the derivative of x depends only on x itself, does not depend on time. If it was like this, that would be not autonomous. And for autonomous systems, we can, as long as we know x dot, and that is sufficient for analysis. Whereas for not autonomous systems, it is not as easy. So for example, what we learned about Lyapunov so far and about stability is eigenanalysis, it had to do with autonomous systems, of course. In particular, what we learned was about systems of this form. All right, so this is autonomous LTI, but here is an kind of the same system, but with what we call input, with U. You already saw this U before in the context of transfer functions, where we had, just as an example, systems like this. And we discussed how U can influence Y, and we had stuff like this, right? Written. Like we discussed how the input influences output. Oh, here's the input. What is output? Well, let's say X is output, like Y equals X. So like all of this is kind of familiar, right? Now, let me just kind of focus your attention on one fact. This system, using eigenanalysis, we can already say it is unstable. Eigenvalue of the system is 2. So it is, its real part is positive. So it is unstable. Also, you can just directly write the solution. The solution is going to be something like e to the power. Probably is not a great idea to try to solve it like I do right now. But I think that is the solution, right? X equals to c times e to the power 2t, I think. And this is a divergent solution. You can imagine the plot would look something like this, or something like this, depending on the value of c. Okay, good. So we can talk about this system for sure. This system is kind of the same, but it has an additional input. And this system, by the fact that we have additional input here, we don't know if it is autonomous or not. Like if U depends on the state, it is autonomous, purely on the state. If U depends on state and time, it is not autonomous. And we don't know if it is stable or not. Stability is a property that we can discuss for autonomous LTIs, not for this type of system. We could also treat U as just input and talk about stability of this particular part of the system, right? And we already know what it is. Stability of this part, we know it is unstable. So that is what we have so far. We know that this is unstable. This as a whole, we don't know. Okay, good. So just to reiterate, we for us is like this is not new. This U here is input, right? But somehow we now realize that it influences stability. At least it can influence stability, because we discuss stability only in terms of this system, not in terms of this system. Okay. Now, if we pick U equal to 0, the result will be unstable. But if we pick, why do I say we can pick it? Well, because let's say it is a control. So it is like, for example, the way a motor behaves. We can program how motor behaves. So we can pick control. And that is pretty much the whole point of control theory, is to pick control. All right, so here, if we pick U as minus 3x, what will happen is, well, after substitution here, this equation becomes x dot equals to minus x. And this is stable. Eigenvalue is equal to -1. And solution is going to just converge. Solution for the system looks like C0 e to the power minus t, unless I'm wrong. So solution. So suddenly, if we pick this control law, the system becomes stable. And that is not something that we so far thought about. But it is, as we can see, it works. And that makes it instantly very, very interesting. So we can use control input U to change stability of the system. That is a big message. All right. Any questions so far?
Everything is clear.
Thank you. One second.
But can our control depend not only on x, I mean current, for example, position, but also on x dot, meaning the velocity of the system or the motor? I just give example.
That is a very, very interesting question. I don't know if you, I don't know if you meant it with as much depth as the question contains. So for what I'm trying to say is that what you said just now is an extremely interesting thing to discuss. In fact, it is so interesting that I would want to spend a little bit of time on that, but it would derail us a little bit from the content of the class. So if you don't mind, we'll discuss it as soon as we finish with introducing the concept. But it's extremely interesting. Can or cannot control depend on x dot? Of course, like you need to remember that x is state, right? So for example, for mechanical systems, the state would include position and velocity, right? So x is itself both position and velocity, right? You remember the substitution that we make. We say x is equal to y dot, let me write it. If we have a mechanical oscillator, for example, we say x is equal to y dot. And you can see control depending on x is the same as control depending on both position and velocity. But x dot is not the same, right? And whether or not it can depend on x dot is extremely interesting. All right, we'll discuss in a bit, but is a very good question. Okay, so stabilizing control. So the definition of stabilizing control is kind of as follows. So the problem of finding control law U that make a certain solution x star of a dynamical system x equal to f xu stable is called stabilizing control problem. So again, we want to find U such that certain solution x star of a dynamical system is stable. Why solution? Well, for linear systems, it is either every solution is stable or no solutions are stable. For nonlinear systems, you can have, how should I put it? Yeah, for nonlinear systems, you can have situations where you have one solution which is unstable, one solution which is stable, and more importantly than that, your control for linear systems acts the same way on the whole solution space, whereas for nonlinear systems, your control may be designed specifically for one solution. So that is why this guy here, like, it feels weird to us because our idea of stability has to do with analyzing f, not with analyzing x star. That's why it looks strange, because we are thinking about linear systems. And in the linear systems, x star doesn't play a role. All right, so that is the definition. Let's just quickly try to understand it in practical terms. Okay, so consider this LTI. This is a standard LTI that we study, right? X equal to AX plus BU. We were a little bit shy about BU so far. From now on, BU is going to be always there, right? Okay, so let us choose control as a linear function of state. We're studying linear control theory, so it kind of makes sense to make it linear, right? So let's just choose it this way. Now, we chose U, so we can substitute this back here. And what we get is this expression. And after opening the brackets, we get this. Oh, notice first, this is autonomous. And second, we already saw systems in this form. There is very little difference between this and this. It's just different matrix. So expression 7 is called closed loop representation. Why closed loop? Well, visually, you can, I don't know if you want to do it, if we want to do it visually though. Let me just try to see if can write it maybe some convincing form. Why closed loop? Closed loop has to do with control diagrams. But yesterday I thought about how we can bring control diagrams to this lecture to connect it with the previous one. And I realized that it just makes everything a little bit more confusing. So I decided not to do it today. It's a little bit hard to balance confusion and usefulness. But anyway, this is a system, right? You can see this is, one equation, which kind of tells you how x dot depends on u. This is another equation, tells you how u depends on x. So you can decide to close the loop, like substitute this here. And that's why we call it a closed loop. So like, what is a loop here? Like, what do you mean by a loop? Is a good question. And on the control diagram, it has to do with feedback control, like with this part that feeds back into the input of the system. But for now, let's just remember, this is what we call closed loop representation. Okay. Now, we have this expression 7, which has to do with control laws that we chose. Okay. Now, observing this system, we notice that we can already analyze its stability. So what we need for stability of the closed loop system is that eigenvalues of this matrix would have real negative real parts for asymptotic stability, or non-positive for stability in the sense of Lyapunov or Martian stability. By definition, if the matrix has strictly negative real parts of its eigenvalues, if the eigenvalues of the matrix have strictly negative real parts, it is called Horvitz. It's a Horvitz matrix. Horvitz is a famous mathematician, famous in signal processing, but also in control theory. And it is useful to remember the name. Like, often enough, saying out loud, matrix has eigenvalues whose real parts are strictly negative takes a while. It also requires this verbal acrobatics that makes you pay attention to what you're saying. And that is just distracting. So much easier to say Horvitz. All right, so this matrix just has to be Horvitz. That's all. Right? And as long as this Horvitz, is our control stabilized the system. By the way, if A is already Horvitz, like if A already represents a stable system, we can just put 0 here and we're done. We don't need any control. So for example, if we have a spring damper system, right? Today is definitely not my day for drawing. I didn't manage to draw a damper. So we have a spring damper system with a motor U attached. We can just put here 0, and that it's still going to be stable. Like, we don't actually need to control anything. The system is naturally stable. That is not very often the case, but sometimes it is. So stability, I don't want to create an impression that K is somehow necessary component of stability. K is just instrument how we can adjust stability of the system, make it stable, for example, if it is unstable. But we don't have to use it. All right, so the game is to find such K that A minus BK is stable. Horvitz. Okay. Any questions so far?
In the case if our A minus BK is matrix more than 1 by 1, so we consider negative it as a negative if all the terms inside of it are negative.
Can you please repeat what is the matrix? You're talking about this matrix, right?
Yeah, I talking about this matrix, and I consider stability a condition for LTI closed loop system.
Eigenvalues, yes. Right?
No, I'm talking about negativeness of its.
No. The stability condition is eigenvalues should have negative real parts.
Okay. We're talking about only eigenvalues. Okay.
Yeah. Elements of the matrix don't have to be negative or positive. That is irrelevant. We only care about eigenvalues.
Okay.
All right. So what we have now is what we have now is this situation with with this situation with control. Like we can try to find control law K such that it is the whole thing is stable. Now like that kind of is that topic is for this type of systems and this type of control, right? As long as we talk about those two, we pretty much exhausted what we can talk about. Like we just need to pick K, that's it. But that is a simple case, and in practice, we don't always. 1 second, sorry. We don't always stick to the simple case. So in practice, sometimes it is more complicated than that. In fact, this simple case is mostly for this trivial solution. So if indeed, if A minus BK is Horvitz, so if it is stable, it means that every solution converges to 0, right? Like for this system, that is what it implies, that every solution converges to 0. So the only solutions that we can stabilize is 0 solution. Okay, just to be clear, right? With this simple control, this is simple system, all we achieve is this solution. Right, but in practice, of course, it's not all that we care about, right? So let's quickly look into a slightly more complicated system. This is called affine. Why affine? Well, because of the constant term here. C makes it affine. What's the example of an affine system? Well, the oscillators that we just discussed is affine, as long as it gravity acts. So if the oscillator was horizontal, I will just drop the damper, just wrote only represented with a spring. This can be a linear system, right? You can write it as a linear system. But if the damper is vertical, and spring damper system is vertical, meaning that gravity acts on it, then it is affine. Remember, the equations for this kind of system would be something like my double dot plus mu y dot plus ky equals to minus mg. And this term, that is this C. C, it doesn't depend on U, doesn't depend on Y. It just a constant term. That we call affine system. Linear means something like this, right? So goes through zero. A line that goes through zero is a linear function. And this type of line is affine. Affine means it doesn't go through zero. So you substitute zero here, you don't necessarily get zero here for affine systems. For linear, you do. Okay. Let me see if I can clear all of this.
Excuse me.
Yes.
In the case of the affine systems, we consider that the, I would say, the matrix U or the vector U is actually in terms of the states, right? In terms of X and XY and X dot, right?
U can be anything still. We will eventually consider U to be equal to function of X. We'll just talk about it in a second. But U can be anything. The affineness or linearness is a property of relations of variables. So like this variable depends linearly on this variable and on this variable. It depends linearly on this variable and on this variable, right? There's a linear dependence between X dot and X and Y, and U. But it also has a constant term. So if it depends purely linearly on all variables, input variables, then it is a linear system. If it has this affine term, so constant term, it is an affine system. That is all. Terminology is just to distinguish between this case and let's say this case. Right. It is useful to distinguish between them because like this, for example, always has solutions that X equals to 0 is always a solution for the system. Not always for the system. So.
Thank you. Understandable.
Thank you for the question. All right. So now we can use, for affine system, we can use affine control law. So this guy. We can use affine control law. Affine control law is different from a linear control law only with the fact that we have some U star here. It's a constant term. We often call it feed-forward term, but control theory, since it is applied science, it also, how should I put it, grows so many terminologies that it is easy to get stuck. We can just call it feed-forward. We can just call it a constant term. Both are fine. You'll see maybe in a bit why. We can discuss at some point if you want why this is not always what we call feed-forward. But the difference would only matter to you if you're going to write an academic paper. Even then, it won't really. So anyway, you have this affine structure. That is what is important. Okay. Now, let's just substitute this control into this equation here. We just want to get this guy into here. Here's the expression that we get. AX stays the same. B times KX minus sign, right? B times U star and C the same, right? So we have this equation 10. It is just those two expressions substituted to one another. Notice that as long as we can pick such U star that BU star equals to minus C, we'll go back to this equations that we know how to work with. X equals to A minus BKX. X dot equals to A minus BKX. So all we need to do is to find such U that BU star equals to minus C. Notice that is not always possible. Obviously, you can find such C and such B that no U star would exist that would map one to another, right? In the same way, you may find such a and B pair, like those matrices may be such that no such K matrix exists that the system will be stable. So trying to stabilize the system may be impossible. Stabilizing the system may be impossible. In the same way as canceling out this term using this term may be impossible. Now, can someone tell me what is the condition, or how we can at least name the condition that BU star equals to C when BU star equals to C is possible? What should be the relations between B and C for this to work?
B shouldn't be equal to 0.
Well, if C is equal to
B
0,
should be invertible.
If B is invertible, then indeed every C would work. But B is almost never invertible. Why? Well, because if B is invertible, control is completely trivial, right? You can, if B was invertible, you can always, for example, choose U to be equal to B to the power minus 1, AX plus C. Let's say plus X dot desired. And substituting this guy into original equation would give us new equation would be X dot equals to X dot desired. Means we can attain every trajectory instantaneously. Like if B is invertible, the problem is trivial. Like we don't have any issues. So B is almost never invertible. Like for example, for mechanical systems, you cannot control speed, or sorry, position directly. You can control velocity, but not position. So already B is cannot be invertible, right? For mechanical systems, it is almost always block of zeros and something here, usually identity matrix. So B is almost never invertible. That is important thing to think about. So what would be the condition for this to be possible? For B and C, what do you think?
Could you please repeat the question?
Repeat the question, right?
Yes.
What should be the relations between B matrix B and vector C for this to be possible? I mean, just I'm not, how should I put it? It's linear algebra, so I'm asking about terminology.
The mathematical answer is for C to be in the column space of B, but I'm not sure if you're looking for that answer.
Yes, that's what I'm looking for. C should be in the column space of B. Indeed, that is a great answer. You can, you can say it should be in the column space of B. You can say in the span of columns of B. Yes. So there should exist such a vector that linear combination of the columns of B would give you C. And that's indeed that's the case. That is not always the case, but as long as what you're trying to do makes sense, it should be the case. Like if for some reason this cannot be made to 0, that means that what it means is that 0 solution is impossible. So you cannot stabilize zero solution. You can stabilize some other solution, but not zero, for example. Okay. By the way, what I just said is maybe sounds interesting to you. Maybe you're thinking, what does it mean? Stabilize some other solution and not zero. Does it mean that there exists some U star constant solution, which is not zero, that you can stabilize here? And indeed, that is the case, right? If this cannot be made into zero, maybe this can be made into zero, right? This whole thing can be made into zero. If C is not in the column space of B, maybe C plus A minus BK X star can be in the column space of B. That's just something for you to think about. We'll, in a few slides, we'll discuss a general approach to this kind of problems. So general approach will just cover everything. But algebra is interesting and simple. So, I think it is extremely profitable for you to try to go through examples like this on your own. Like, just consider this problem, right? Let's say this cannot be made into zero. What can be made into zero? Just ask yourself, what is the solutions? What is the space of X star solutions, or states for which it can be made into zero? How I can find this space? That is just linear algebra problem, and you can solve it. And it is very interesting. And studying those problems was actually the way to understand this topic better. All right. That is what I was talking about what happens when this is impossible, but when it is possible, when BU can be made to BU star can be made into minus C, it cancels, and we get our original equation, and we can stabilize zero solution. All right. Before we go on to the next slide, I would suggest a 5-minute break. It is middle of the lecture. I'm trying to learn to look at the time during the lectures, so we won't delay tutorials again. We'll have a 5-minute break, and then we'll resume. Thank you, Devlat. It's very, very important. So we forgot to record, and now on the YouTube, we are not going to have a discussion of the beginning of trajectory tracking. So whoever follows with us on YouTube will have to, I guess, open the slides and just go through this and this on their own, like this and this. Okay. Now, our next step is to introduce the concept of control error. This is still part of the same problem. Like so far we only discussed how we find U star. U star could also be given to us, right? So it's not even a part of the problem. Now we're actually trying to solve the problem. Again, remember what we want is to stabilize arbitrary trajectory, arbitrary solution, X star equals to X star of time of t. We introduce control error. What is control error? It's the difference between current solution and desired solution. This solution, we call it desired solution. This is an actual solution. So the difference between them is a control error. And we want to, we'll just have to work with it. Like it is, control error is extremely useful. Why is it useful? Well, if control error goes to zero asymptotically, it means that every solution goes to X star. Why? Well, if this goes to 0, it means that x goes to x star, right? So that's it. Please notice that while this is like a couple lines where we just introduced some new variable x minus x star, coded control error, and noticed obvious fact that if it goes to 0, then x goes to x star. This couple lines is sufficient for us to solve arbitrary trajectory following. Why? Well, for good reason, because suddenly, instead of trying to stabilize some arbitrary solution, well, what we will be able to do is to stabilize E equal to 0 instead. And that is what we have been doing the whole time. So let me just show you.
Excuse me, sir.
Yes.
Okay, before we go further, I want to, how to say, I'm still not really not sure about the difference between x and x prime or x
star.
Yes, I mean,
what is the difference? Okay, let's try to see how we can explain the difference between them. So what would be a good answer? Let's go to the whiteboard. I think that is the important enough point to discuss on the whiteboard. So let's just try. So let's consider extremely simple case. X dot equals to x plus u. Scalar case. So that is just equation, right? Like OD, we can solve it exactly, right? The solution would be like C0. I'm not going to write solution. Okay, well, you understand, right? We could write it out.
Yes.
Okay. Now, what could be a solution to this equation? One possible solution. Well, one possible solution to this equation can be something like, let's say, cosine t. You may say, whoa, stop.
So we want this solution. We want somehow to modify the system until we have this solution as the new system.
Give me a little bit of time. I will explain.
Okay.
So you can tell me, please stop. Like this doesn't look at all like a solution to this equation. The solution to this equation would have strictly real eigenvalues, and this just doesn't look like it. But in fact, it can be a solution. Let me prove it to you. So x dot star would be equal to minus sine t, right? If this is x dot x star, its derivative is minus sine t, right? So what we have is minus sine t equals to cosine t plus u star rules. So u star would just have to be equal to minus sine t plus cosine t. That's it. So with this u star, this is a solution. So the solution is just a cosine wave. Okay. Now, what is x star of 0? Can someone tell me?
Should be
Yeah,
one.
it is 1.
It is 1, right? Okay. Now, this is the solution. And the solution starts at 1. But now I'll tell you that initial condition of our original equation is equal to 1/2. Is there a contradiction? Like we didn't say what initial conditions are, right? But now so because we didn't say it, we could just invent solutions like this, right? But now somehow I'm saying, okay, initial conditions is 1/2, not 1. What's going on?
We can just add constants, I guess, to the.
Yeah, we could, but how should I put it? We're not going to. Like, this is a perfectly legit solution for this system, just from a different initial conditions. So, and initial conditions, we never know them in practice. Like, this is one initial condition, but maybe it is, in some other case, it would be -0.3. Who knows? Right. So what we care about in Lyapunov stability, remember, when we discuss stability, we discuss Lyapunov stability, right? What we care about is that from every initial condition, like initial condition 1, initial condition 1/2, initial condition -0.3, everything converges to the same. Like, here we had this cosine wave. So what we care about is everything converging to this cosine wave. Everything converging to this cosine wave. As long as it does, this cosine wave, the solution is stable. If it doesn't, if something diverges, then it is not stable. All right. So basically, what I'm trying to say is this solution is not a representative of all possible solutions. It's just one solution, which is possible with particular choice of U star, with particular initial conditions. Is great, right? That's nice. Of course, change initial conditions, it's no longer valid as a solution for new initial conditions, but it was valid for its initial conditions. And that's what all we care about. We don't care about initial conditions when we analyze stability. What we care is convergence. We care about is convergence. So we want every solution to converge to the solutions that we're analyzing. So as long as everything is converges to this solution, we are perfectly happy with with it being just one specific solution. Okay, so now you can see also the difference. X of t is those red solutions, the ones that we are analyzing for convergence. X star is this blue solution to which everything should converge. Did you get it now?
Yes, so in other words, is we choose the X star, how to say, if we have certain purposes to achieve,
yeah,
we
choose it, or someone gives it to us.
And the U star is chosen accordingly, or at least estimated as close as possible.
U star, we can try to estimate it, or someone can give it to us as well.
Oh, okay.
For our purposes, we can think of it as often enough. We can think about it as given, but we can try to just find it, of course. Okay, good. But the reason I'm saying it is given, it kind of feels cheap, right? You would say, yeah, if stuff like this is given, then what is, life is easy, right? But there is a good reason why we can say it is given, because often enough it comes from outside of control theory. For example, mechanical equations, there is just a separate topic that allows you to specifically find U star, like inverse dynamics, for example. Often enough, engineering process is designed with what we call, how do we call it? nominal behavior. Like there is a nominal, for example, like nominal speed for a motor, nominal torque consumption, nominal voltage. And those nominal things represent a solution. So often enough, what I'm trying to say is U star is just given to you by engineering practice or from a specific field. Often enough, you don't have to invent anything because other people invented those solutions already. And that is a reasonable approach to take. So, again, U star, don't sweat it too much. Okay, I think we don't have a lot of time, so I will just try to be a little bit quicker. Okay, now we have two equations. This equation, x dot equal to ax plus bu, and the same but for x star. X dot star equals to ax star plus bu star. We can find the difference between them, subtract this from this, one from another. So the difference is going to look like this. Now, we remember that E by definition is x minus x star. So this is just E dot. This is AE dot, AE. And we will introduce another notation, V equals to U minus U star. That is not a, like hashable, is okay, is whatever. We don't have to introduce it, but it looks cleaner. And with that, what we arrive at is this equation. E dot equals to AE plus BV. What is very interesting about this equation is first, this is LTI. Second, as before, of course. Second, it is the same LTI that we just discussed in the beginning of the lecture. And thirdly, what we care about is to stabilize this solution. Sorry, E equals to 0. We just want to stabilize trivial solution. And we already saw how to do it, right? Let me just go back a little bit. Like look at this. Like here, when we discussed this equation, we were talking about how this has to be Horvitz. And we said that what we are stabilizing is actually the solution. Well, that is what we want to stabilize here. With this equation, what we want to stabilize is trivial solution, E equal to 0. Okay. And as long as we stabilize it, what we achieve is that, well, how do we stabilize it, by the way? Well, we can, it will be on the next slide, but we can just pick V equals to minus X E, and we will get E dot equals to A minus BK E. And that would mean that E goes to 0, and which in terms means X goes to X star. So X star is stabilized as a solution. We stabilized E, we stabilized X star. Okay. So every trajectory will converge towards X star, and control error will converge to 0. That's very, very interesting. That is also, same as a lot of things here. We leave some details out, but let's just concentrate on what we have done here. Is already extremely powerful. All right. Oops. Let's just quickly go through what we did here. So with this equation, we stabilize 0 solution, use this control law, and that's it, right? Closed loop, I've already wrote it on the previous slide. It was A minus BK, closed loop solution for the system. But now, this control law, we can actually open it up. we remember what this is, right? It is U minus U star. So U minus U star, and E is X minus X star. We get this here, and we get this here. And what we get is this equation. And that is extremely popular and classic. That's what you find all the time in textbooks, in papers, everywhere. It's a typical formulation of a control. You can see you have this familiar K matrix here. Here what you have is the difference between your actual position or state or whatever and the desired state. So this is an error, control error by definition. Sometimes people write it as E, but often enough people just keep it like this. So you say you have your current position and you have your desired position. Find difference, multiply by K, and add your constant term. This is often called feed-forward term. This is often called feedback term. Why feedback? Again, because we feed back the information about current state. This is often measured by sensors. So you can imagine you have the process, you have a measurement, and the measurement of the process goes all the way back into the input. Like the measurement is, you would think of it as output. It goes back to the input. All right, so this is a very popular way of defining it. Let me just quickly look in the next slide. So, as I said, this we call it often feedback, and this we call feed forward. You can notice that feedback somehow includes this X star. Sometimes people would prefer to just say, okay, we have some part which is just minus kx, and we have another part which is just minus k. So it will be plus k x star plus u star, which this would be not autonomous part, so something that depends on time, and this will be purely autonomous part, something that only depends on the state. So you sometimes people would like to distinguish between them, like keep everything that depends on the state in one side, everything that depends on time on the other side. But you don't need to worry about those kind of things. Just keep in mind that this is something that people can discuss. But yeah, feed-forward part usually is solved separately from feedback part. Here, all you need to find is k. X star, you usually already have it. X star in robotics, you can think about it as finding trajectory, inverse kinematics, this type of things is where you get X star from. K is stabilizing control problem. Finding K is a part of stabilizing control. Finding U star is, again, in mechanics, it's inverse dynamics, for example, trajectory generation. So those finding X star, K, and U star is 3 different problems. And what we care about most here is just finding K star or K. X star we definitely don't care about. It is completely field specific. U star, I gave you one tool, but please remember it is just one tool. How much time do we have? Like 5 minutes or no time? Someone tell me, please.
10 minutes.
10 minutes. Great. Okay, we'll try to be on time. All right. So what we just did was we learned aerodynamics, which is extremely important tool, very, very powerful, allows us to stabilize arbitrary trajectories. Of course, we did it for a linear system. What if we had C here? Would it be much different? Well, it wouldn't be. It is. It's kind of just all the same thing. So first of all, this would still be the case. Why? Well, because the solution, right? So if X was a solution for the system, then this would be the case. Then we do the same trick, introduce E as X minus X star. subtract this from the original equation, and you get this equation here, because C will just cancel out. And you can try to do this to find U star, but again, U star, often enough, you just have it given to you. All right, so that was easy. That was easy, and notice, please, that we got this affine result pretty much for free. Didn't introduce new complexity. Now, sometimes we also have this interesting different thing, which is called point-to-point control. And that is when instead of solution, what we get is just X star. We say, please go to this X star. You can think of it as a like more, how should I put it? It's easy to understand, I guess. You just tell your quadrator, please go to the coordinates 10, 10, 20, right? Makes sense. You're not going to tell to your quadrator, please follow trajectory defined by this equation, right? So this kind of makes more sense. Of course, actually, your quadrator will not be able to do this task. It's if you tell it go to 10, 10, 20, it's just going to fall down. You have to give it trajectory. But this trajectory is generated in the software. So in the software of the quadrator. So you know, they save you from a lot of trouble. But you can kind of think of it as would have been nice if we could do it, right? And for linear systems, you can. In fact, all you need to do is to just say, okay, this is just new trajectory where X star is constant and this is equal to 0. And then you just do trajectory, you know, aerodynamics trick, exactly the same as before. So you still write E equals to X minus X star, V equals to U minus U star. You write this E dot equals to A E plus B BV. Still write V as minus K E. And then to find K, you just call like place on A, B. That's it. So you don't really need to do anything different here. Like it is a different approach to control, you can say. Instead of giving it a trajectory, you just give it a final point, but just treat this final point as a trajectory. And that's it. Like we get it for free. That is a nice thing about controls, that as long as you understand one idea, there are usually dozens that we get for free. In the last year slides, we had like 10 more slides with the same examples. Like, for example, we had a, I will write it here for completeness because maybe your TAs will introduce it to you. For example, we were asking, what do you do if you want to have your U in this form, minus X plus U star, or let's say plus U0. Notice we don't have X minus X star here, just X. What do you do if you want it in this form? Well, it's easy, right? Like you can imagine it is going to be easy to answer this question. Like U would probably be like U star plus minus plus KX star, etc. There are a lot of those tricks that we can do just by algebraic analysis of this thing. So, but I deleted those slides because you know, we're already out of time, right? And if we had 10 more, we just wouldn't be able to do it. All right. So here is a couple of suggestions for what you can do on your own to self-study. My main suggestion would be to just do a couple of examples in Python and get the feeling of it, like especially with place. We will have it in practice soon enough, I think. So don't worry about it. You will get to practice finding control law. And also make sure you understand the terminology. Like the only difficult thing in this lecture was terminology, like Horvitz, aerodynamics, etc. Everything else I think is relatively simple. All right, and soon enough we're going to expand on it. From now on, I think almost all lectures will giving you more details about how to control systems. Like analysis part, we already passed it. Like eigenvalue analysis, representations, we passed it. Transfer functions on the state space. Now we're going to discuss control every lecture. That means that the terminology I introduced today is going to be repeated every week. So if you don't understand something, it's a good time to ask or go through the slides. On the other hand, you can be sure that we are going to have less jumpiness between topics and more concentration on this. So that hopefully will be a little bit easier. All right, I will stop with that. So we will have a slight break before tutorial. I'll end the call, and I will create a new call for the tutorial session. Is there any questions before we finish? I think no questions. Okay, you can write me in the chat if you have some questions that just don't want to, spend time with your colleagues who want to take a small break. All right, thank you for coming, and sorry again for the online format. See you later, guys.
Goodbye. Goodbye. Thank you. Goodbye.
Bye.
Goodbye.